Hello, chemistry students. Today we are going to talk about predicting products. So in order for you to keep up with this video, you are going to have to stop and grab your periodic table and your list of common polyatomic ions. Okay. Write the complete balanced equation for the following. Potassium iodide in an aqueous solution reacts with chlorine to yield something. You're going to have to predict that. The first step here is we're going to write out the products. So we have potassium iodide. Okay, from the periodic table, you can see that potassium is a group 1 element and iodine is a group 7 element. So we have a charge of +1 and a charge of -1. Drop and cross those charges and you'll get a 1-to-1 ratio. That will react with chlorine, which is a gas. And remember, this is one of our Hankel-Briffs. So if it's by itself, it will exist with a buddy. Okay. Now, looking at this setup, it looks like it's going to be a single displacement reaction. And chlorine is a group 7 element, just like iodine. So chlorine will replace iodine, and iodine will exist on its own. Again, we have a +1 charge and a -1 charge, so dropping and crossing gives us another 1-to-1 ratio. And we have another Hankel-Briff. Okay, there you go. So that's how you predict the products. And now we need to balance the equation. We have 1 potassium on each side, 1 iodine on the left, 2 on the right, 2 chlorine on the left, and 1 on the right. So in order to balance this, I will need to put a coefficient in front of potassium chloride. And another coefficient in front of potassium iodide. Okay, there you go. Balanced. Okay, this one is asking us to predict the products for strontium fluoride reacting with silver nitrate in an aqueous solution. So start with your periodic table. You've got strontium and fluorine for our first molecule. Strontium is a group 2 element, so it has a charge of +2. And fluorine has a charge of -1 because it's a group 7 element. So we'll have to drop and cross those charges to give a neutral molecule. So the 2 will come down and the 1 will come down, but we won't write that. Okay, so cleaning that up a little bit, SRF2. Okay, that will react with silver nitrate. In this case, silver does not have a Roman numeral next to it, so we are going to say it has a charge of +1. And nitrate is one of your common polyatomic ions. It has a charge of -1. So if you drop and cross those, you'll already have a neutral molecule. Okay, so we have 2 cations and 2 anions here. So when they react, They're just going to switch partners. Okay, so we've got strontium nitrate as our first product, and silver fluoride. Strontium has a charge of +2, nitrate has a charge of -1, so you'll actually need 2 of those nitrates in order to balance out the strontium. And then silver and fluorine are each a charge of +1, so that's neutral. Okay, so we have 1 of each of our cations on both sides. Two fluorines to 1 nitrogen, and 2 over here, 3 oxygen, and 6 over here. So I'm going to start by balancing my nitrogens and oxygens. I'm going to do that by adding a coefficient in front of silver nitrate. Okay, so now I need to add a coefficient in front of silver fluoride. There you go. Balanced. Okay, last one. Methanol reacts with oxygen. Okay, so this one I want you to take a close look at. Luckily, I gave you the chemical formula for methanol, and it's reacting with oxygen. So this is a combustion reaction. And you know, in a combustion reaction, the products are always carbon dioxide and water. So that's easy. If you can figure out that it's combustion, you already know what the products are going to be. Don't forget that oxygen lives with a buddy. Okay, so what's not always so easy about combustion reactions is balancing them. Don't be surprised if you have to use larger coefficients than normal. I'll show you what I mean. Okay, so we start with carbon. There's 1 on each side. Hydrogen has 4 and 2. And oxygen has 3 and 3. So it's almost balanced to start with, but these ones can get kind of tricky. So we're going to start by adding our 2 to balance out our hydrogens. So now we have 4, but now with our oxygens we have 4. Okay, I like to leave this oxygen alone when I'm balancing a combustion reaction because it's the only one with an atom all by itself. So it's the last one I'm going to update, okay? So let's add a 2 in front of methanol. So now we end up with 2 carbons over here, 8 hydrogens, and now we have 4 oxygens. So you see, we're kind of back where we started, where we're almost balanced, but these hydrogens are messing us up. So we're going to have to change this into a 4. So that's the only way to update the hydrogens on the right side. So that will change this into an 8. And oxygen is now a 6. Okay. Now carbon, we need to balance the carbons, so let's just add our 2 here. Our carbons are balanced, and that bumps our oxygen up to an 8. Righty. So this is where I wanted to get it. Right now, the only thing that's unbalanced is the oxygen, and there aren't enough of them on the product side. So now we just have to change the coefficient. That's easy to change. It's only going to change one of our variables. Okay, so we need to go from 4 oxygens to 8 oxygens. There are 2 of them right there and 2 of them here. So let's add a 3. And that will change this to 8. All right. So that is the balanced equation. Now, if you ever think that your coefficients are getting too big, there's an easy way to check and make sure that this is correct. You need to look at all of the coefficients. So we've got 2, 3, 2, and 4, and make sure that there is not one common denominator between them. Make sure they can't be reduced. So if you can divide every one of your coefficients by 2, then you've gone too far, and if you divide them all by 2, it'll still be balanced. The proper balanced equation is the one with the lowest whole number ratio for the coefficients. And in this one, we have 3 even numbers and 1 odd number. So there is no way to reduce this. So this is the correct balanced equation. It looks kind of messy like this. If you want to, you can rewrite it. But I can tell what this means.